All right. No more questions? Really? Okay. If there are no more questions, we can always move on to chapter 21. We can get started on chapter 21 unless somebody has a question.
Um, could you re-go over question 2?
Question 2.
The 2 middle parts for B.
These parts right here.
Mm-hmm.
All right, so here we have a 92 gram toy car, which would be a mass, right? So we have our mass, and of course we want to convert that to kilograms, so that's 0.092 kilograms. It's going to have to accelerate from rest to 1.7 meters per second using its two 1.5 volt batteries. So we know the final velocity, for example, is going to equal 1.7 meters per second. And that means we can actually calculate the kinetic energy because kinetic energy is equal to 1/2 mv squared. So we can use our mass and our v and square it, plug it into that equation and get this part. Now this part right here is the thing that is more involved with this semester. Assuming 100% efficiency, how much charge is used up from the battery? Well, potential energy, electrical potential energy, is going to be equal to negative the kinetic energy. And I don't think they actually care about the negative sign in this. I think they just want to know the numbers here. But this is also equal to Q, the amount of charge, times the potential difference. And that potential difference is right here, 3 volts. Right? And so if we know what the kinetic energy is, which we do from in this first part of part A, then we can set the kinetic energy equal to Q times V and solve for Q. So what we do is we take our Q, well, we solve for Q here, and we get Q equals the kinetic energy, which is 1/2 mv squared, and divide it by Q, divide by V, not Q, divide by V, where V is the voltage, big V is the voltage. This is big V, and little v is the velocity. So that ends up being 1/2 mv squared divided by v, which you could also write as m little v squared, or velocity squared, divided by 2 times the voltage, big V. And in fact, you use this same equation, but you use this part for part C right there. You use a similar equation here, but instead of using Q equal to like a number of coulombs, you use it equal to a number of electrons. So if you have 1 electron moving through 12 volts, then that equals 1 electron volt. Instead of multiplying Q times V, you just say, how many number of electrons do I have multiplied by V? And if you just have 1, then it's 12 electron volts for this particular problem right there. 12 eV. So, any more questions? No more questions?
You could go over 11.
I could I? I suppose I could. Wait a second. 11 is no, I don't want to do that. What I want to do is go back here. Open this up. 20. So this one is a bunch of multiple choice questions, right? So we're defining three things here. And only one of these is correct on each of these. So probably the best way to do it is to go through and determine which ones aren't the correct thing. What do we know about potential difference? What is potential difference? What is not potential difference? We know some things like, and you could go directly to the book and find the definition. But we know, for example, that potential difference is equal to charge. No, it's equal to potential energy per unit charge, like that, because U equals Q times V. In this case, V equals QU divided by Q. So we know that. Well, I don't want to just tell you the answers, but there is a clue in these that two of the answers that are in here, that are in this group, are actually the answers to this one and this one. So I think the best bet to do this is to just go look up in your book potential difference. Go search for that phrase right there, and go read what the definition is. Go search what current is, right? Go search what electric resistance is. If you search for those three terms in your book, you will be taken to a paragraph in the book that tells you in no uncertain terms what each of these are, and it will be pretty easy to figure out what the answer is, I think. Because two of these five answers are definitely not this, because they're one of these other ones. And the other ones, are maybe a little bit tricky, but are not necessarily too difficult to rule out, I don't think. So I guess that's what I can tell you about question 11 without just telling you the answers. Do you have any other questions about number 11?
Do you think you could put more tries on there for question 11?
How many did I put on? I don't remember.
It said there are 3.
Okay. I think I could give one more. If I give 2 more, it makes it a little too easy. But I think I can. I don't know if I can actually change it while it's being done. I might be able to. Let's try that. Maybe, I don't know if I can. That's a good question. I'd have to go and look. That's taking current delta weirdness. Looks like it'll be okay if I do that. So yeah, we can do that. All right, any other questions? No more questions?
13.
13. Okay, so we know that current is defined specifically as charge going by in time. So this one is current equals charge divided by time. It's pretty simple. You just have to charge, you have to divide, you have to solve it for the charge essentially. And then you're just plugging these numbers in. There's no conversion at all. That's just the definition of current. When you're looking up your question, when you're looking up your answers for question 11, write down the equation for current, and then you'll use that one here. Any more? All right, well, let's go ahead and take a few minutes to get a little bit started with chapter 21. If you have any more questions in chapter 20, feel free to email me. I will be available for a few hours this evening. Let's go ahead and take a look at chapter 21. There's some good stuff in chapter 21. Whoa. In chapter 21, we're going to take circuits to a whole new level. And then we're going to start off with resistors. Now, we already talked about capacitors somewhere, didn't we? Can't remember if we did or not. Yeah, we did. We talked about capacitors in series and in parallel. Well, resistors have a very similar kind of thing going on when you put them in series and parallel, except it's exactly the opposite. Remember that resistors, when they get longer, get bigger. And so if you just put resistors in parallel, one after the other, that's just like making a longer resistor. So when you put resistors in series, they add together just like normal. You just add them. For 4 ohm plus 5 ohm resistor, it gives you a 9 ohm resistor when you put them in series, one right after the other. Remember that in series, you can't have any branches going off in any other directions in between anything. They just have to be one right after the other with no branches off anywhere. And so adding them together is simple. Resistors in series, add them 1, 2, 3. And they give all the reasons behind that, which have to do with Ohm's law, but it's really quite simple. So resistances add just like normal math in series. When they're in parallel, however, they do just like the capacitors did in series, because when resistors are in parallel, what happens is the current splits up, and some of the current goes through the first resistor, some goes through the second, some goes through the third, and so on. And the overall result is that more current can actually get through it. It's like having 3 lanes instead of 1 lane, right? So more current can get through, and this resistance in parallel behaves like a resistor that's smaller than the smallest resistor in the whole series, well, in the whole parallel grouping. And the math for it is just like the capacitors in series. because the currents all have to add up to equal the overall current, and you use Ohm's law to go through this again. The details aren't really all that important for you, but in the end, the total resistance of resistors in parallel is 1 over resistors in parallel equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3, and so on. So in this particular example, we have 3 resistors, 1 ohm, 1 ohm, 6 ohms, and 13 ohms, and there's a 12 volt voltage. They're connected in parallel with a 12 volt like battery or something like this. And we want to know the total resistance of these resistors. Well, we add 1 over R1 plus 1 over R2 plus 1 over R3, and we get this value of 1.2436 over ohms. Well, that's not a resistance, that's an inverse resistance. When we take the inverse of that, 1 over this number, in other words, then we get the actual resistance of those 3 resistors combined in parallel of 0.8041, which is smaller than the smallest resistance, which was 1. And so we get a total resistance that's smaller, and then you can plug that resistance into Ohm's law right here with the voltage of 12 volts and calculate the current. That's the total current coming out of the battery, 14.92. And those 14.92 amps have to split themselves between these 3 resistors. Part of it goes here, part of it goes here, part of it goes here. And it turns out that it splits itself. It puts most of the current through the smallest resistor. So resistor 1 was the smallest at 1 ohm. Most of the current will go through this one because the smallest resistor resists the current the least and allows the most to go through. Resistor 2, which was the 3 ohm resistor, allows more current, less current than the first resistor, but more current than the last resistor. So, and then the last resistor allows the least amount of current because it was the biggest at 13 ohms. So most current through the smallest resistor, second most current through the second smallest resistor, least current through the biggest resistor, and that total current was what we just calculated. If you add all 3 of those currents together, that total current was this total current of 14.92 amps. So you can actually calculate the current through each one of those resistances by using Ohm's law with the 12 volts with each resistor separately. So for the current going through the first one is 12 volts divided by 1 ohm, which is 12 amps. The total current was 14.9 amps. So this is definitely most of that current. Through the 6 ohm resistor, which I said was a 3 ohm resistor, it's actually a 6 ohm resistor, you get 2 amps of current going through that one. 12 volts divided by 6 ohms gives you 2 amps. And then for the third one, 12 volts divided by 3 ohms gives you 0.92 amps, and that's by far the least amount of current that goes through any of these 3 resistors. You add them all together and you still get that 14.92 amps. You can also calculate the power separately through each resistor by doing the voltage squared divided by the resistor using V squared over R, one of the power equations. And you find out that most of the power is dissipated through that first resistor, less power is dissipated through the second, and the least amount is dissipated through the third. So then when you get into these situations where you have a bunch of resistors like this, you can simplify this. These 2 are obviously in parallel because they're connected on both ends. These 3 are obviously in parallel, connected on both ends. You can use the parallel equation to combine these into a single resistor right there, and these 2 also into a single resistor here. And then all of a sudden, you've got these 2 that are definitely in series where you can add them together to get one combined resistor for those 2. Then these 2 are in parallel, so you can combine those using the parallel equation. And then you get these 2 which are in series, you can combine them, and you've now simplified a fairly complex resistor network down to a single resistance with a single voltage. And then once you've got it to this point, you can actually calculate the total current going through this whole thing. And then you can backtrack to get the voltages and currents across each resistor. And this is the beginning of what we call network analysis, where we try to figure out what is going on everywhere in an electrical circuit and find out the current going through everything, find out the voltage across everything, find out the power dissipated everywhere, and then we can design the circuit properly to handle the kind of loads that it's going to receive. So they're going to do this in this example here and do that kind of thing here and so on. And then we'll take that into the next section next time tomorrow to do some more advanced things. We'll do that example that we just looked at. We'll do it in step by step. We'll do this example step by step and go on to the next section next time. So have a great day. Remember to email me if you have any more questions on chapter 20. Try to get that finished up tonight, and we will see you tomorrow. Have a great evening.